Hello everyone, I'm Bongjoon from KAIST. Today I'll be presenting our work on pathfinding future PIM architectures by demystifying a commercial PIM technology. This work was done by myself and my colleagues Taehun Kim, Dongjae Lee, and Professor Minsoo. Let me first explain the motivation of our work. Processing in memory, or PIM, has been explored for decades by computer architects, and with the advent of critical memory-intensive workloads like AI, several commercial PIM technologies have been introduced to the market, ranging from domain-specific PIM architectures to more general-purpose PIM architectures. In this work, we categorize PIM designs based on their level of programmability. Domain-specific PIM designs like Samsung UPMEM PIM or SK Hynix AIM-X are designed to accelerate matrix multiplications, primarily targeting AI workloads. However, general-purpose PIM designs like UPMEM PIM are able to accelerate a broad range of PIM applications as they come with their own set of programming languages and fairly sophisticated software stack, enhancing their programmability. So why the emphasis on programmability? Introducing a new computing device to existing computer systems require a non-trivial amount of changes to both hardware and software stack. So having the right level of flexibility and programmability that future-proofs its applicability is critical, which is why this work focuses on the industry's first general-purpose programmable PIM device, UPMEM PIM. In the rest of this presentation, we seek to uncover UPMEM PIM's unique characteristics from a computer architect's perspective, which we utilize to find interesting architectural features that we deem will be critical for future PIM architectures to support. So what does UPMEM PIM look like? Let us first briefly review the UPMEM PIM architecture. UPMEM PIM complies with standard DDR specs, so it can be plugged into current computing systems and work with other conventional DDR memories. Like conventional DDR memory, UPMEM PIM has 8 chips, each of which has 8 DRAM processing units, or DPUs, which are RISC PIM cores. The DPU has a control and status interface and a DDR4 interface to communicate with the host. Inside the DPU, there's the register file, pipeline to execute instructions, SRAM memory, and DRAM bank. A DPU resides right next to each DRAM bank, therefore there is one DPU per DRAM bank. As such, an UPMEM PIM system can have thousands of DPUs amounting to 0.896 TOPS of compute throughput and 2.5 terabytes per second of memory bandwidth. The DPU is an in-order 14-stage pipelined processor with its own RISC-based ISA. It can concurrently execute up to 24 threads and has its own local instruction memory called IRAM and a scratchpad memory called WRAM, which caches data with high locality from the DRAM bank called MRAM. Now that we know the basic architecture of UPMEM PIM, let's look into UPMEM PIM's programming model. UPMEM PIM's programming model is similar to today's GPU programming. UPMEM PIM follows the coprocessor computing model, where the CPU offloads the memory-intensive task to the DPU, functioning as an arbiter of the PIM program's execution. More specifically, the host splits the input data across multiple DPUs. Then after computation, the host gathers the output results from thousands of DPU and makes the final output data. Now let's see how we can program this general-purpose PIM hardware by looking at the actual vector addition program. Like GPU programming, we need host-side code and device-side code as well. UPMEM PIM follows single program multiple data, or SPMD, for concurrent thread execution. That means each thread is executed concurrently, working on a different piece of data. First, the host allocates DPUs by calling the DPU alloc function and loads PIM kernels to the DPUs by calling the DPU load function. Then, the host transfers data to DPUs by calling the DPU push exfer function. The host sends commands to DPUs to execute the PIM kernel by calling the DPU launch function. Within each DPU, the device calculates the pointer address of the input data located in MRAM and allocates memory on the heap region of each DPU by calling the memallocate function provided by UPMEM. Then, the DPUs read the data sent by the host by calling the MRAM read function. This will generate DMA instructions that load data from the DRAM to the scratchpad memory WRAM. After the data is ready, the device can compute the input data vector addition in this example. The results can be written to the DRAM banks by calling the MRAM write function. Later, the host can gather across multiple DPUs MRAM to retrieve the final result of the vector addition. As briefly mentioned before, the DPU uses DMA instructions to load store data to and from MRAM. This is different from CUDA. In CUDA, the same load store instructions can read or write data to or from scratchpads and DRAM. However, UPMEM PIM needs different instructions to access scratchpads and DRAM. UPMEM PIM uses load store instructions to access scratchpads and DMA instructions to access DRAM. Moreover, DPUs use compiler-generated physical addresses as is without virtual memory. When the host sends or receives data to or from DPUs, it uses a pointer called DPU MRAM heap pointer, which is the physical address at the end of the program binary. The application programmer carefully stacks input and output data by using this pointer address. So far, we talked about what UPMEM PIM and DPUs look like and how they can execute the PIM kernels. Now let us talk about our UPMulator simulation framework, a cycle-level simulator that targets UPMEM PIM architectures. Our simulation framework can use application and library source code written in UPMEM-C as is, as we have seen earlier in the vector addition example. We use UPMEM's open source compiler called DPU UPMEM DPU-RT Clang, which is based on the LLVM framework. This compiler generates assembly code that is written in UPMEM's own ISA tailored for PIM. The front end of our simulation framework conducts lexical and syntax analysis to construct abstract syntax tree. Then the linker figures out how the application should be linked with the UPMEM libraries. The linker and assembler generates binary files in ones and zeros that the backend can understand. The reason why we implement our custom linker is because UPMEM's linker aborts when the binary exceeds the physical limit of IRAM or WRAM. This can degrade the flexibility of our simulation framework. Moreover, as we will explain later in this presentation, thanks to our linker, we could explore a variety of different research topics because we can map any portion of the PIM kernel to any memory type. The backend models the DPU microarchitecture based on publicly available microarchitectural details released by UPMEM. The backend is an event-driven simulator whose functional correctness is verified over real hardware using the PRIM benchmark suite. Now let's move on to an in-depth analysis and characterization of the UPMEM PIM architecture using our simulation framework, UPMulator. As mentioned before, we used an open-sourced PRIM benchmark suite that can run on UPMEM PIM to evaluate UPMulator. The PRIM benchmark suite consists of 16 data-intensive workloads from various application domains such as linear algebra, graph processing, neural networks, and etc., for which we use different input data sizes for evaluating single DPU and multi-DPU based experiments as shown in this table. This figure shows the compute and memory read bandwidth utilization of the PRIM benchmark suite. The x-axis is the benchmark names with 1, 4, 16 threads, and the y-axis on the left is compute utilization, and the y-axis on the right is memory utilization. The red line shows the compute utilization, and the blue line shows the memory utilization. As you can see, compute utilization is generally higher than memory utilization except for binary search, or BS, and sparse matrix vector multiplication, or SPMV. The same tendency can be observed in this figure too. The x-axis is the same as before, and the y-axis is the latency breakdown of each DPU state. The issuable state, colored in black, is when the DPU is able to issue and execute an instruction, and all other colors, red, yellow, and blue, are situations where the DPU is not able to issue an instruction due to off-chip memory excesses or structural hazards within the DPU microarchitectures. When we break down DPU's runtime, when executed with a sufficient number of threads, 16 threads in this experiment, we can observe that under many applications, the DPU spends the majority of its execution time executing instructions rather than waiting for the data to come back from DRAM. Again, this means that while PIM-suitable applications are generally memory-bound on conventional hardware like CPUs or GPUs, when they are run on our UPMEM PIM architecture, the applications start to be more compute-bound. We also characterize the PIM benchmark suite's various runtime behavior, but due to timing constraints, we ask you to refer to our paper for more details. We also characterize the PIM benchmark suite under multi-DPU configurations. The x-axis is the benchmark names with 1, 16, 64 DPUs, and the number of threads per DPU is 16. The left axis shows the latency breakdown of each stage, and the right axis shows the speed up. The kernel, colored in black, shows the portion where the DPUs are running the PIM kernel. All other colors, red, blue, and yellow, are time spent transferring data between CPU to DPU, DPU to CPU, and DPU to DPU. For data transfers to occur, UPMEM PIM SDK utilizes AVX vector load store instructions to explicitly move data across two separate CPU memory space and the UPMEM PIM address space. Because such data transfer latency cannot be overlapped with the PIM kernel execution time across multiple DPUs, the system-wide performance is dominated by data transfers. On the other hand, in NVIDIA GPUs, the programmer can overlap host-to-device or device-to-host data transfer time with kernel execution time by using CUDA streams. We believe that a future version of the UPMEM hardware-software stack that supports flexible kernel partitioning and task scheduling, similar to NVIDIA GPU's CUDA stream, can help alleviate such inefficiency, one which we believe can be a good use case of our UPMulator for architectural exploration. Now that we have covered the in-depth characterization results of the current UPMEM's PIM design, let us move on to our discussion on how we believe future PIM architectures should evolve to become better first-class compute citizens within the overall system. Today's commercial PIM processors employ a simple in-order pipeline without any sophisticated microarchitectures to extract ILP for higher performance. For instance, they do not have superscalers, super pipelining, or fancy branch predictors. Such a wimpy PIM processor design point leaves significant performance left on the table, as conventionally memory-bound workloads now fall under the compute-bound regime with PIM. While such a design decision was inevitable because the current generation of PIM processor is fabricated on a density-optimized technology node. Future PIM architectures with more flexibility in area, power, and thermal budget can certainly consider relatively more aggressive, performance-oriented design points with higher operating frequency and ILP-enhancing microarchitectures. In this case study, we use UPMulator to see how much performance can be unlocked in PIM's compute-bound workload by augmenting UPMEM PIM's DPU with ILP-enhancing optimizations. In this figure, the leftmost base design point is the vanilla UPMEM PIM architecture, and we incrementally add more advanced microarchitectural techniques as we move from left to right. Specifically, we incrementally add advanced data forwarding solutions to better handle pipeline hazards, higher register file bandwidth to reduce structural hazards at the register file, a two-way superscalar pipeline, and finally a 2 times higher DPU core operating frequency. For heavily compute-bound workloads like those highlighted in red in this slide, we can see significant performance improvements with such ILP-enhanced PIM architecture, with modest performance improvements being observed for modestly compute-heavy workloads colored in green. And not surprisingly, for those workloads that are still memory-bound even under PIM colored blue, the benefits of ILP-enhanced designs are less pronounced. Overall, many data-intensive workloads exhibit a compute-bound behavior when executed with PIM, and we believe enhancing PIM's computational throughput will likely become much more important in future PIM designs. Another feature we believe will be critical in future PIM architectures is the support for multi-tenancy. Multi-tenancy is one of the most important features for processors to provide for cloud deployment, as it helps better saturate the processor's compute and memory resources, reducing its total cost of ownership. As such, current CPUs and GPUs come with a variety of hardware-software features that support multi-tenancy with performance isolation and security guarantees. Given UPMEM PIM's abundant compute and memory throughput, having proper multi-tenancy support will be vital for future PIM architectures, especially when seeking for industrial adoption by cloud vendors. Unfortunately, our case study reveals that current commercial PIM chips, whether it be UPMEM PIM or domain-specific PIMs, are not able to meet the requirements of a multi-tenancy, not just from a hardware-software perspective, but also from its programming model's perspective. Due to timing constraints, let us focus our attention on 2 important conditions to be met for multi-tenancy. First, collocated workloads should be securely executed without interfering with each other. To enable such a security feature, one of the fundamental architectural support that is needed is isolating the memory address space of collocated applications using MMU's address translation capability. Practically all commercial PIM systems are designed without an MMU, as UPMEM PIM uses physical addressing. Therefore, collocating multiple workloads with address space isolation is fundamentally impossible in MMU-less PIM architectures. In this case study, we add a hardware MMU to UPMEM PIM using our UPMulator and study its performance implications. Our MMU model employs a single page table walker, the page size of which is 4 KB, and is backed with a single-level 16-entry fully associative TLB. We utilize such a mechanism to translate all DRAM accesses from its virtual address to its physical address and measure its performance regression. Overall, an MMU-edited PIM experiences an average performance loss of 0.8% with a maximum of 15.1% by adding address translations to DPU's memory accesses. Such low performance overhead is mainly attributed to UPMEM's scratchpad-centric memory model, where data transfer across DRAM and scratchpad are orchestrated in coarse-grained chunks whose size is in the order of several kilobytes over DMA instructions, exhibiting high spatial locality and thus achieving high TLB hit rates. Overall, our analysis reveals that enhancing security guarantees of PIM through proper MMU support, which is a necessary condition to enable multi-tenancy, is practical as it incurs reasonably low performance overhead. However, even if UPMEM PIM does have an MMU, there is another significant problem that needs to be resolved. Since UPMEM PIM only supports scratchpads without a cache, when 2 PIM applications are to be collocated and they each require more scratchpad memory than the physical limit, the system will crash. Consequently, collocating both of these workloads require a non-trivial amount of changes to both collocated PIM programs to make sure the aggregate scratchpad usage fits within the physical limit, arguably an acceptable requirement to enforce to end-user application developers. In other words, collocated workloads must not be aware of the fact that they are concurrently executing. Supporting transparency to collocated applications therefore cannot be honored under UPMEM PIM's current scratchpad-centric programming model. Therefore, we believe that to properly support multi-tenant execution in PIM, not only on MMU but more importantly, a user-transparent cache architecture support is needed. Putting things together, our previous case study motivated the need for future PIM to also employ on-demand caches rather than single-handedly relying on scratchpads to guarantee transparency to multi-tenant workloads while still providing the ability to reap data locality benefits. That is, PIM programs running on top of an on-demand cache will be able to leverage data locality in an opportunistic manner while not having to change the program itself. To this end, in this final case study, we implement an on-demand cache and compare its efficiency versus the original scratchpad-based PIM execution by modifying our linker and backend simulator. The modified linker maps binary files only to the DRAM bank, and the modified backend simulator is augmented with an instruction and data cache in between the processing core and the DRAM bank, capturing locality in an opportunistic manner. In this figure, we compare the performance of UPMEM PIM using only scratchpads, colored in red, and UPMEM PIM using only caches, colored in blue. The y-axis shows the speed up when the performance of the scratchpad-centric design is normalized to 1. Our results show that some benchmarks are faster with caches, while other benchmarks are faster with scratchpads, which is expected. But our intention with this case study is to highlight the fact that on-demand caches, when used properly, can still perform competitively for PIM-based designs as well, allowing collocated application to not worry about right-sizing its scratchpad usage, thereby guaranteeing transparency to end-user PIM programmers who seek multi-tenant deployment of PIM applications. Lastly, we open-sourced our simulation framework UPMLater on GitHub, which can be accessed through the GitHub link at the bottom. So here are the 3 key takeaways from our work. In this paper, for the first time, we developed a cycle-level simulator targeting the industry's first general-purpose PIM architecture, conducting a detailed characterization of real PIM benchmarks. Using this simulator, we conduct several case studies that uncover interesting research directions for future PIM architectures, for instance, supporting ILP-enhancing microarchitectures, multi-tenancy, and on-demand caches. Our hope with this work is that our open-sourced UPMLater will help broaden the scope of the research that PIM architects can explore. Thank you for listening to our presentation.